So, hello everyone, welcome to this Men&Mice webinar. My name is Peter Peterson. Today's webinar is focused on DNSSEC. Carsten, is this just like a general DNSSEC webinar you present today?
This is an introduction webinar, so it's for people who haven't really worked with DNSSEC before, and it's a tutorial that shows how easy it is to make the first step, that is to sign a zone, and we will build on top of that in future webinars.
Very good. So please note, everyone, that all attendees are on mute, but we encourage you to submit questions through the GoToMeeting control panel. We are also recording this session, and you can find this webinar along with the slides and on our website within a few days. At our website, you can also find recordings and slides from previous webinars and information on our training offering and so on, not to mention our product itself, IP address management solution. So if you drop off this call, you can always pick up where you left, from our website. So Carsten, the audience is yours.
Thank you, Peter. So hello and welcome everybody to our DNSSEC signing tutorial. So we will talk today about why we want to have DNSSEC, and then we have some decisions to make, basically what algorithms to use, what key size to use if we choose the RSA algorithm, and whether to use NSEC or NSEC 3. And then I will show how to sign a zone with DNSSEC using bind 9 and doing the same with the not DNS server. Both DNS servers make it extremely easy to start with DNSSEC. But first, what is this DNSSEC about? DNSSEC is an authentication layer for DNS data. Basically, with DNSSEC, the data that is in DNS gets digital signatures, and these digital signatures can be used to guarantee the authenticity and integrity of the data, meaning that we, as a consumer of the DNS data, can be sure that the data comes from the right owner and that the data has not been changed on transit. DNSSEC does not encrypt data in any way, so it doesn't provide any privacy. The DNS data is still plain in the open, and everyone can see what is asked for and what answers are coming back. The IETF is actually working on the second part, meaning that they work on extensions to the DNS protocol to also provide privacy, but that will be something for the future. It's not ready yet. Why do we want to have DNSSEC? The original goal of DNSSEC is to protect the DNS data, to protect against cache spoofing, meaning an attacker injecting wrong DNS information into a DNS resolver cache, which can have horrible effects because that can be used to divert IP traffic and can redirect people to phishing sites, to drive-by malware and similar nasty things. It can also protect against man-in-the-middle attacks. It can protect against a takeover of an authoritative server. So if an attacker breaks into your authoritative DNS servers and makes changes to your zone, without the private key, the attacker cannot sign the changes, so the changes will not be accepted if the zone is DNSSEC signed. And then also to guard against rogue secondaries, meaning if you don't operate your secondaries yourself, but you have a service partner that runs your secondaries for you, you are sure that this service partner does not make any change to your zone content, and it is serving only the content that you have approved. Also, in the near future, DNSSEC will be able to protect authoritative DNS servers against denial of service attacks. That is a new thingy that is currently being debated in the IETF and probably will be finalized next week during the IETF in Chicago. And that will allow then caching servers to stop certain kinds of denial of service attacks, especially the random subdomain attacks on authoritative servers. So that is the first time DNSSEC also helps against denial of service attacks. And also DNSSEC enables quite a number of new security features like mail transport security. We have spoken about this in this webinar series before. Mail end-to-end encryption with either PGP or SMIME, opportunistic IPsec encryption, SSH server authentication, and even the certification authority authorization, the CAA record that prevents a certification authority to issue certificates in your name, even if you don't have a business relationship with the certification authority. So that can all be done with DNSSEC. DNSSEC is almost universally available in the world. Everything that is green here on this world map has already DNSSEC. There are a few white spots in Africa and a little bit Asia, but most of the world already has DNSSEC enabled and up and running. So a little bit about the fundamentals of DNSSEC. This is DNSSEC in a nutshell, a very condensed view on how it works. On the left side, we see the authoritative server, and that is what we will do in this tutorial, that is signing a zone. We have the plain DNS data, which is the green box, and that data is being hashed. Every resource record, every little tiny data that is in the DNS zones will be hashed with a hashing algorithm like SHA-256 or SHA-512, which will generate a fingerprint, and that fingerprint will then be encrypted with the private key. And that will generate a signature, the so-called resource record signature. And both the data and the signatures will be stored in a regular DNS zone file along with the public key that matches the private key. And once that is done, we declare the zone as being signed, and that is what we will do today. Now, to continue this picture, the DS record, which is the hash of the public key, will then be published in the parent zone, and that will create a chain of trust that can be validated by the receiver of the data to make sure that the data is really origin and authentic. Going on the right side, if a consumer of DNS data, which might be an application or might be a DNS resolver, receives DNS data, it receives the data plus the signature. It then takes the signature, fetches the public key that belongs to that signature, and decrypts the signature with the public key, recreating the fingerprint. And the fingerprint now is exactly the same fingerprint that is seen on the left side that has been created by hashing the data. At the same time, the validator is fetching the DS record from the parent zone, making sure that the public key is really the correct public key and has not been tampered with. So this detour through the parent zone is an extra security measure, because an attacker now, in order to exchange the key material, does not only need to infect and compromise your DNS server infrastructure, but also the server infrastructure of the parent zone, which is in most cases a top-level domain, and that is much harder to do. Also, the top-level domain is secured by its top-level domain, which is the root zone, and an attacker would also need to compromise that one. So that's quite a challenge for an attacker. That makes DNSSEC so secure. Once we have validated the public key, we calculate from the DNS data that we have received with the same hashing algorithm our own fingerprint, and then we compare the two fingerprints. The fingerprint that we have calculated and the fingerprint we have decrypted by the public key. If both are exactly the same, we have proven that the data has not been changed on the way, and also it must come from the owner of the private key, that is the owner of the domain name. And that means we have validated the data. In order to use DNSSEC, we have a choice of multiple DNS server products. We can use Byte 9, Byte 9.6 and up. Usually we use today Byte 9.9, 9.10, or the latest one is 9.11. We can use NSD from NNet Labs. We can use Windows, either Windows 2012 or 2016 DNS Server, which is a good authoritative DNSSEC server with a GUI. We can have Power DNS. Power DNS has also been shown here in this webinar series before, and not DNS, which we will also show today. Before we start DNSSEC signing, we need to make some decisions. For example, what kind of keys do we use and what algorithms do we use? And we have quite a choice of algorithms here. And on this list is all the algorithms that are defined for DNSSEC. Now, the first two, MD5 RSA and SHA-1 RSA, are not recommended anymore. The first one was already broken before DNSSEC was standardized, so that was never been implemented. And SHA-1 is officially now broken, completely broken, since 3 weeks ago, when Google managed to get the first real SHA-1 collision. So don't use these. RSA SHA-256 is the recommended today. Also in green we have ECDSA, which is the elliptic curve digital signature algorithm, which is also recommended today. We have RSA SHA-512, which is good, but creates rather large keys. That is the downside. We have DSA, the digital signature algorithm, which is slow in validation, has no extra security, and because it is so slow, it's like 5 times slower than the RSA and the other algorithms. Nobody really uses that. We have ECC GOST, which is mainly used in Russia because it's mandated by the Russian government. Then we have ECDSA, which is also a very recommended algorithm here, and quite new. Since last year, we have the Bernstein curve ED25519 and the Edwards curve ED448. Both are good, but because they are so new, there's almost no DNS software out there that supports these new curves. So we have to wait maybe 3 or 4 more years until we really can use these new curves in production in the internet. Which leaves us with RSA SHA-256 and ECDSA for the moment. Here is, and this is just for reference, the algorithm numbers in the first column, then the algorithm's names and the mnemonics for that. The mnemonics are important when you create key material with the DNSSEC keygen command line tool from bind, because then you need to give this mnemonic. ECDSA versus RSA in the com zone. Last week at the ICANN meeting in Copenhagen, Roland van Rijswijk from SurfNet, which is the Dutch university network, gave a presentation about a really interesting research they'd done in February this year, and that is about the algorithms used in .com zone. And most .com zones today are still signed with RSA SHA-1 and SEC3. But more and more are now also signed with the elliptic curve ECDSA, and this is mostly because larger hosting providers like Cloudflare choose ECDSA for their DNSSEC implementation. And ECDSA has almost surpassed RSA SHA-256 by now, almost. RSA SHA-256 has a tiny little more amount of zones being signed, but probably in the next weeks, ECDSA will surpass it. So ECDSA is just fine for now. But if you use RSA algorithms, you also have to think about the size of the keys. With the elliptic curve algorithms, the key sizes are already fixed because they are part of the algorithm. But for RSA, we have to think about the key algorithms. Now, RC 6781, which is the DNSSEC Operational Practice version 2 document, recommends 1024-bit RSA key. Now, this is currently being thought as being not state-of-the-art anymore. The root zone and also new zones that are currently signed, they use 2048-bit keys, both for the key signing key and for the zone signing key. And I have here some other defaults that I sometimes use when signing DNSSEC zone, which is the mildly paranoid version of 2560-bit and the zone signing key of 1536-bit. Now, while with other crypto algorithms and other users of the RSA, the bit size always needs to be doubled, like 1024, 2048, and then 4096. That is not the case with DNSSEC. You can just use any number of bits in the DNSSEC keys. It doesn't need to be always double. And even if you have one more bit, the security of the key almost doubles. So having a mildly larger key is even better than having just a 1724 key. So at the moment, it is said that RSA keys less than 700 bits are just easily breakable. And in 2012, someone calculated that a 1024-bit RSA SHA-1 key can be broken or might be broken in 5 years. That is actually now this year. So this is the recommendation to move away from SHA-1, and this prediction really holds because this year Google has managed to break SHA-1. And it is said that SHA-256 and SHA-512 with 2048-bit keys or larger will be safe for the next decades. Based on the current crypto analysis. That means if not, something really new will be found, a new way to attack this crypto. So also keep in mind that if you have larger keys, that means more computing power. If you double the key size, the time to create the signatures will increase in a factor of 8, and the time to validate the signatures will increase by a factor of 4. Probably the second time, the validation time, is what you should be aiming for. Don't use too large keys, because it might be then an extra burden on the users that try to validate. In order to keep the DNS package sizes in a reasonable size, if you use the bind name server, it's highly recommended to only sign the DNS key set, the keys itself, with the KSK only, and not with the ZSK, which would be the default with bind. And that can be done with the option DNSSEC DNS key KSK only, yes. And you put that in the option block just in the beginning of your named.conf. What's the problem here? Currently, there's a problem with IPv6 and fragmentation. We had a webinar on that already some month ago. And just as a refresher here, there's currently a problem if UDP packages are sent over IPv6 that are larger than 2,280 byte, because that they may fragment, and these fragments might be dropped while traversing the internet. So it is recommended to keep the size of the packages below that number over UDP and switch to TCP on the larger. If you are interested in this, learn more about this, I would recommend to search for the webinar on this topic that we had a few months ago. So last decision that we have to take is whether we use NSEC or NSEC 3. What is this NSEC or NSEC 3? It's a way to do authenticated denial of existence. It's in DNSSEC a way to prove that something doesn't exist in DNS. It proves the negative answers. And there are currently two implementation. One is called the NSEC, and the other one is the NSEC 3. And there is one on the horizon called NSEC 5, which is currently being standardized. Both or all three have its pros and cons. And if you are in doubt, choose NSEC. Here I have a table of the pros and cons. NSEC is quite fast in the overall processing, both in signing and also in validation. it's human debuggable. That's important. If you have a problem with DNSSEC, you want to figure out manually as an administrator what's going wrong with NSEC, it is possible to do that. The downside, the con for NSEC is that it allows zone walking. That means anyone from the outside can list the content of your DNS zone. That for in the first impulse, it sounds like a security problem, but usually it isn't, especially if it's a zone that has just common content like mail server, some text records, some address records for the web server, mail server, and such. And even without zone walking, it is usually quite possible to enumerate, that is to list the zone content by just brute force asking the namespace. And with NSEC 3 actually makes zone walking harder. It does that by hashing the domain names, but it requires hash operations for every negative answer. That is a burden on all authoritative servers that have the zone, and it's a little bit slower because both the validation side and the authoritative side need to do some hashing calculations. And it makes zone walking not only harder, but it doesn't prevent it really 100%. And the upcoming NSEC 5 will prevent zone walking completely. So that is a good solution for everyone who wants to have privacy and doesn't want the zone to be listed. But at the moment, it's just an internet draft. It's not implemented in production DNS servers, so we cannot use it at this point of time. But it is something to look out for the future. So now we come to the tutorial. In this tutorial, we will use the algorithm ECDSA 256P256 with NSEC 3 using bind 9.10. And with NOT, we will use the RSA SHA-256 with NSEC. I've created template files for this tutorial that you can download on our GitHub. So you don't need to type the configuration files and the zone files. So first, with bind 9, we have a configuration file that we put in place. It starts with an option block, which contains the global configuration. Because it is an authoritative server, we disable recursion with recursion no. We define a key directory where we want to store the DNSSEC keys. And we enable DNSSEC with DNSSEC enable yes. Then we have a larger logging block. If you are interested in bind 9 logging, that was the topic of the January webinar. You can find a recording on that bind 9 logging webinar still on YouTube or on our website. And then at the end, we have the zone definition for dnssec.example.com. It's an inline signing zone, and it has automatic DNSSEC maintenance, meaning that the bind name server will automatically re-sign the zone if needed. And inline signing means that after signing, you can just manage the zone file as a normal zone. As if without DNSSEC, you just can go in the zone file with the text editor, make your changes, increment the serial number, don't forget about that, and then reload the name server, and it will automatically re-sign the zone with DNSSEC and publish your changes. This is the zone file that we use. This is our dnssec.example.com file. It's just a very simple zone file with time to live of 1 hour, SOA record to NS records, text record, and address record for the web space. So both in place, we can make sure that our DNS server works and answers on requests. Here we see it answers on the SOA record request, but there are no signatures. Even we ask with plus DNSSEC, so the zone is currently not signed. It's an unsigned zone. We create the directories for the keys and make sure that the keys are owned by the user account that runs the bind name server. Then we create the keys first the zone signing key and then the key signing key. And we make sure that the keys also have the permissions that they are owned by the bind process. And once the keys are in place and in the correct directory, we just need to sign the zone with RNDC sign name of the zone. Then we enable NSEC3 with RNDC signing -NSEC3 parameters. We give the parameters here. And after that, the zone is signed and everything is done. So that's easy. Once we have the zone signed, we can check that it is actually signed. We see the RSA-Key, the signatures. If we ask for the zone entries plus DNSSEC and plus multi, we see that here in this response from DIG that the SOA record has actually a signature. And then we need to create the delegation signer record for the parent zone to create the chain of trust. We can use that with the DNSSEC DS from key command, and we point that command towards the public key of the key signing key. And that will spit out the DS record that we can then put in our registry interface or send it by mail to the registrar that does the registry business for us. So I have created a small video recording on how this works. So here I first check out the template files from Git. And then there is a directory, one for bind and one for not. I copy the namely.conf, which is the configuration file in the etc directory, and copy the zone file DNSSEC-example.com into the var namely directory. With namely-checkconf, I test that the configuration is actually sound, no errors in there. Having a quick look at the configuration here. This is the global part, and then the logging part. And below we have the zone configuration. And the zone file looks quite good. Now this zone file already has an NSEC3 parameter record in there, but that's not required. The parameter will automatically put in with the RNDC command. I'm starting bind here, make sure it is successfully started. And the zone here is actually already noted as being signed because it has inline signing yes. But without the keys, the signing process just failed. That is the red line we see here. And if we ask for the SOA record with plus DNSSEC, there's no signature on there because it is currently not signed because there are no keys. So now I'm creating the key directory and generating the zone signing key. The algorithm is ECDSA P256 SHA-256. It's a zone key, and it should be stored in var namely keys. That is the destination directory, and it's for the zone DNSSEC.example.com. Creating ECDSA keys is usually quite fast if you have enough randomness in your system. And I just execute the same command for the key signing key. Now we have two keys, and I adjust the permissions on the keys so that the named process owns the keys and can read that. With RNDC sign, the zone gets signed. It's now signed, and in the second part, I enable then the NSEC3. Here's the signing again. And then with RDC signing, NSEC3 param, and then the hashing algorithm for NSEC3, which is SHA-1, no opt-out, 100 iterations, and the salt in hexadecimal. I forget to type in the name of the zone. So it's DNSSECExample.com, the zone to be signed. Now it's successfully signed, and now I send a query towards the local DNS server. Plus DNSSEC plus multi, and in this case we see the signature, and it's a nice little small signature because it's an elliptic curve algorithm being used here, and that creates rather small signatures. With DNSSEC DS from key, I generate the DS record. Here we are. It's algorithm 13 for key 57658. I can copy that over to the registrar that puts that in the zone of my parent domain. Now this was signing with bind. Now we have a look on how that works with the not DNS server. This is the configuration file from the not DNS server. It's a global configuration that lists the IP addresses and port where the server should be listened on. That is all IPv4 and all IPv6. And it should run as the user not and the group not. It logs everything to syslog from severity info and up. And what's special here is that we specify the DNSSEC policy in the configuration file. While with bind, the algorithm and the key sizes are in the case. Here we specify that in the configuration file. We give the policy a name called RSA-SHA-256, and it's for algorithm RSA-SHA-256. And we have a key signing key of 2560-bit and a zone signing key of 2048-bit. And then below, we have the zone definition for the domain dnssec.example.com. It lives in var.lib not zones. That is the directory where we find the zone file, and the zone file name is dnssec.example.com zone. And we have DNSSEC signing on, and we use the policy with the name RSA-SHA-256. So we can have multiple policies and define or connect the zones with the different policies in our configuration file. This is the zone file, very similar to the zone file we have seen before and we've used with bind, nothing special here. And we reload our NOT server, or we start it, and then in syslog we see that the server has automatically picked up the new configuration. NOT automatically creates the keys in the background. We don't have to do that manually, and it starts signing the zone with the key signing key and zone signing key, and it prints out the key tags, the key IDs, the algorithms in the log file. It also automatically increments the serial number. And if we send a dig command towards the local DNS server, we now see that we have a signature on the SOA record here. And this signature, if we compare that to the ECDSA signature, is quite large. So this is 404 byte already, and the biggest part is the signature because we are using RSA-SHA-256. So I've also prepared a video for that, how to do the zone signing with NOT. So I already checked out the configuration file, and I copy that into the user local etc directory, because I've compiled NOT from source and not from a package. That is the content of the configuration file, the global part, the logging information, everything is written to syslog, the DNSSEC signing policy, and one zone file that we load. Then I copy the zone file over to the directory varlib not zones. And I start the journal, which shows me the syslog. There was some old error messages in there that was from previous attempts. And I start the not daemon, which is the not server here. And in syslog, we see that it successfully has signed the DNSSEC.example zone. And if I now dig for DNSSEC-example.com server record, I get an answer back, and it has the serial 1005, and it has the SOA resource record signature in the response. So that was successfully signed. Now for creating the DS record from NOT, we can also either use the DNSSEC DS from key from the bind tools, or from the LDNS utility, the key2ds. We use dig here to get the key signing key out of the zone and write that into a file, dnssec.example.com ksk, and then I use LDNS key to ds. -2 gives me just the SHA-256 hash, and -n prints the data on the screen, and then I specify the file which contains the key signing key, and the command prints out the delegation signer record, the DS record, on the screen. And I can copy that now over into the registry interface and complete the chain of trust. Now we have a signed zone. What's next? What can we do now? Of course, you should publish the DS record via your registrar, bring the DS record in the parent zone in order to close the chain of trust that anyone outside can do DNSSEC validation. You should test your DNSSEC validation, for example, with the excellent DNSVis website, which tests the chain of trust and tells you whether your zone is correct or whether you have DNSSEC issues. And then you can decide whether you want or need a key rollover. You might have heard that key rollovers is really the hard thing of DNSSEC, and that's true. The key rollover is the real challenge. Signing a zone is quite easy. But even without key rollover, a DNSSEC signed zone is still more secure than a plain non-DNSSEC zone. So even if you shy away from key rollovers, you should still sign your zones. If you don't want to do a key rollover, you are just fine. You can just keep the zone signed as is, as shown here, for the next years, and you don't need to touch the DNSSEC parameters at all. Just make your changes to the zone content, reload your name server, and everything is fine. If you want to do key rollover, we will cover key rollover and the automation of key rollover in an upcoming webinar. So that concludes today's tutorial of DNSSEC signing. But before we enter the answer and question section, let me tell you a little bit about our upcoming DNS trainings. We will have a DNS training in Redwood City that is already booked. We have a few seats available. So if you want to join last minute, please let our colleagues from the training department know. And also we have on the East Coast in Boston a training May 1st to May 3rd. And the advanced and DNSSEC training is also in the 1st April week and the 1st May week, Redwood City and Boston. And then in Germany, we have the DNS bind training, the next one end of May, and DNSSEC and DANE special training in December, both in the Linux Hotel Essen. And you see here a picture of Linux Hotel in summer. I really recommend joining there. It's a very relaxed place to learn. And our next webinar will be on SMTP, strict transport security, versus SMTP with DANE. This is a more email-y subject, but also makes use of DNS. That's why we cover it here. It will be on April 13th, Thursday again at 5 p.m. European Summer Time or 3 p.m. GMT. Okay, let's see if we have any questions.
Very good, Carsten. Thank you. So I've got a couple of questions for you already. Maybe first, now that Windows 2016 comes out with like a better DNSSEC support, I'm just curious, have you seen any pickup on that front? Do you think this will help, in overall deployment of DNSSEC?
Yes. Of course, there are companies that rely on Microsoft software, and they have good Microsoft server expertise. And for these companies, it really makes sense to deploy DNS servers and DNSSEC signers with the new Windows 2016 server. It's a really good implementation, I must say, of DNSSEC in the Windows server.
Well, I know you are from the Unix world, Carsten, so this is quite a compliment you give there. There must be a reason.
Yeah.
Excellent. Now, everyone on this webinar, please note you can submit your additional questions through the GoToWebinar portal. But another question I have, Carsten, is we are slowly getting there towards general usage of DNSSEC. One missing piece there, or I may be wrong, but I find it like a missing piece. That is the cloud DNS offering. There's a number of cloud-based DNS services out there, and I'm seeing organizations sometimes moving their external-facing DNS to these cloud offerings. Are we seeing DNSSEC integrated into these offerings yet?
Yes, I see that. For example, Cloudflare, one of the big website hosters, and I would count them to a cloud offering. They started providing a very easy DNSSEC implementation for all the DNS zones they host for customers. It's now in the Cloudflare interface. It's just a button that you have to check mark, and then your zone is DNSSEC signed. So they don't do it automatically. As a customer, you just need to log in to your Cloudflare account and then hit the button, and then you are secured. And, after Cloudflare started with that, we now see a couple of other hosters to follow suit. And once that is implemented, it's then quite easy, and we see a lot of uptake. And that is the reason why already after just a few months, ECDSA is now taking over RSA SHA-256 in the COM zone. This is because of Cloudflare, because it's so easy, and they have so many customers that it's just the sheer number of people now enabling DNSSEC on the Cloudflare system that makes a big influence on DNSSEC deployment.
That's very interesting. So, Carsten, I'm not seeing any further questions here, so I think we'll put an end to the webinar for now. But I would like to remind everyone that the slides and the recording from this webinar will be available from our website. We'll probably get a notification when it's ready for downloading. But I think thanks everyone for joining. And Carsten, thank you very much.
There's one more question that just came in.
Yep, there it is. Carsten, you can maybe address that one.
I just need to read. The question is, if you use a cloud-based DNSSEC implementation, once you click go, how long before the DS record actually gets published and we go live? Now, that depends on the time to live and the speed of the interface of the top-level domain. So I know from COM and the German DE zone, it's usually about an hour it takes to publish the DS record there. There are other top-level domains where it can take up to 24 hours. And I know that Cloudflare is actively working with the registries from top-level domains to make that faster. Because one goal of these cloud solutions is, of course, to make it as immediate as possible for the customer. If a customer clicks on a button, the customer wants to see the effect immediately. And that requires still some negotiation between the registries, but we are coming there. Currently, I would say with the most top-level domains, especially the new ones and the big generic and country code top-level domains, about an hour. And then we should see the DS record published.
Excellent. Very good, Carsten. Anything else you want to address for now?
No, I'm fine.
Well, then thank you again, and I hope I will see everyone on this webinar showing up on our future webinars as well. So thank you guys and girls, and have a nice day.
Thank you.